I thought it would be nice to work some of these problems from our review, from our worksheet 5 AP type problems with you on video. So if you had any questions and couldn't get to tutoring, that you could see how what my thought process is in going through these. All right. So in number 1, we see in FRQ, part A, we are sketching the slope field on the 9 indicated points. So I'm grabbing my straight edge and something to write with here, and let's see, here's our differential equation that gives the slopes. So this is what's giving the slopes. Alright, I'm going to start with the point 0, 1. 0, 1. Well, when x is 0 or when y is 0, the slope is going to be 0. So on the axes, the slope is always 0. So I'm going to come over here, do my 0 slopes whenever x is 0. We don't have to do it when y is 0, so I'm not going to do it. They're only asking for the 9 indicated points, and that's these 9 points. Okay, let's go over here to where x is 1, y is 1. We're going to have 1/2, which is up 1 over 2, or down 1, left 2. I'm going to do it that way so that I have something to line my straight edge up on. At the point 1, 2, I'm going to have 2 over 2, which is 1, so that slope is going to be a 1. Up 1 over 1, or down 1, left 1. And then at the point 1, 3, I'm going to have 3 over 2, which is up 3 over 2, or down 3, left 2. Like that. Okay? At the point -1, +1, I'm going to have -1 over 2, so down 1 over 2, -1/2. Like that. -1, 2 will be -1, and -1, 3 will be -3 over 2. So there is my slope field at the 9 indicated points. All right. Part B, use Euler's method with 2 steps to approximate f of point 2 given that f of 0 is 3. So here's our starting point. Here's our differential equation, which will give the slopes. The only other thing I need before I begin is my delta x. So what is delta x? Well, I'm starting at 0, and I'm going 2 equal steps to get to point 2. So delta x has got to be a point 1. So every time before you start, you need your initial point, you need your delta x, and then you need something that's giving you the slope, right? In this case, it's an equation. All right, so my first slope at the point given to me is going to be 0 over 2, which is just 0. So my equation is y minus the y value is my slope times my delta x. So y is 3. So my first stopping point, f of point 1, I'm starting at 0 and I went up point 1, that function value is approximately 3. Now we're going to find our new slope, dy dx at our new point is equal to 0.1 times 3 divided by 2, which is, think of it this way, I'm going to multiply, if I multiply top and bottom by 10, you guys, to get rid of that 0.1, I'm going to have 3 over 20, right? And that's fine, 3 over 20 is fine. Another way that we could have done this is made that a 0.3 over 2. 0.3 divided by 2, you're taking half of 0.3, which is 0.15. So that's fine too. Either way is fine. You can write it, you could have left it like this. That's fine too. In an FRQ, you could totally just leave it like that. Not a problem. Y minus the y value is equal to the slope, whichever one of these you want, times delta x. And then y will be 3 plus 0.1 times 0.15 is 0.015, or you just leave it like that. Remember, this is a safe stop spot. So now f at our final x value is approximately 3 plus 0.015, which is 3.015, and that's our answer. But just remember that you can totally safe stop on these, okay? So if you don't want to multiply those decimals, you don't have to, unless it's multiple choice, of course. All right, find the particular solution. Big points. Okay, big points. Find the particular solution to that differential equation with the initial condition f of 0 is 3. And then use your solution and a calculator to find f of 0.2. Your test in my class is not going to be with a calculator. Okay? FYI. Alright, so here is the differential equation. First step is to separate. Separate and then integrate, right? So I'm going to separate. I'm going to divide both sides by y. I'm going to multiply both sides by dx. So I'm going to have 1 over y dy is equal to 1/2 x dx. So that's separated. That's worth a point or 2 on my test. Now we integrate. Antiderivative of 1 over y, natural log y, is equal to antiderivative of 1/2 x is 1/4 x squared plus c. I've got to see your antiderivative, you guys. So the separating is worth a point. On my test, I'll double that. The separating is worth a point. The next point is given for your antiderivatives. You've got to show me your antiderivatives. So don't be skipping steps here. Show me your antiderivative. Okay? Now I'm going to e to both sides. When I e to both sides, I get y is equal to c e to the 1/4 x squared. If you have forgotten why that is true, go and watch my video for the review, the in-class review. Okay? But that is true. All right, now I'm going to plug in my point. F of 0 is 3, so 3 is equal to c e to the 0, and e to the 0 is 1, so 3 is equal to c, so y is equal to 3e to the 1/4 x squared. We're done. Now we found the particular solution, and now we're going to use our particular solution to find f at point 2. Okay? F of 0.2 is 3e to the 1/4 times 0.2 squared, right? Well, that would be a safe stop spot right there. Why do you think they wanted to get us for us to get the value here? Let's find the value first while you think about that question. 3e to the 1/4 times 0.2 squared is 3.03015. Okay, why do you think they wanted us to find that? They wanted us to compare that with our Euler's approximation of the same thing. So that we found the same thing by Euler's method, right? And there was our approximation using Euler's method. Here's the actual value. So it wasn't too bad of an approximation with only 2 steps up there. All right. How would they finish scoring this one, you guys? They would give 1 point for finding C. They would give 1 point for solving for Y there. Okay. And then I'm sure they would give 1 point for that approximation in that problem. Okay. For Euler's method, it's usually worth 2 points. 1 point for the first step and 1 point for your answer. Sometimes they give a point for the form of Euler's method, the 2 distinct steps of Euler's method. Okay, so keep that in mind. You need to show all your steps. And then in this case, that's 5, 6, 7. So this would be worth 2 points on the exam, if this was a question on the actual exam. Okay. All right. Number 2. It says if dy dt is negative 2y, and if y equals 1 when t equals 0, they're giving us an initial point, an initial condition. Find t when y is a half. So I'm going to take this and solve that differential equation. Yeah, that's what I'm going to do. So dy dt is negative 2y. Separate and integrate. 1 over y dy is equal to negative 2 dt. Integrate. Natural log absolute value y is equal to negative 2t plus c. Okay. Now, when y is 1, t is 0. When y is 1, t is 0. Right? Since I get to plug 1 into a natural log and make it a natural log of 1, I'm going to go ahead and do that now. So y equals 1. When t equals 0, I'm plugging those in. I'm going to get 0 is equal to 0 plus c. So I get c is 0. That just leaves me natural log y is negative 2t. Right? So now I want to find t when y is a half. So when y is a half, I'll have natural log of a half is negative 2t, right? So t will be negative 1/2 natural log 1/2. Is that a possible answer up here? No, it's not listed. So they must have played with it. They like to play with natural logs. Well, one thing that they would do is they would, if it's a negative, sometimes they'll move that up to the exponent. So if they did that, it would be 1/2 natural log 1/2 to the negative 1 is 2. Is that one of our choices? Ooh, this was close. But ours is positive, not negative. But that was close. There it is right there. There it is right there. ln 2 over 2. That's it. See. I thought maybe I was going to have to move this to the exponent as well and make that natural log of the square root of 2. But that wasn't listed as an option. So sometimes they'll make you play with those natural logs using your log properties. So beware of that. Be ready for that. Know those log properties. Okay. At each point xy on a certain curve, the slope of the curve, so they're giving us dy dx, is equal to 3x squared y. If the curve contains the point 0,8, then its equation is, they're asking us to solve the differential equation without coming out and explicitly saying, solve the differential equation. They're asking for the equation of the curve, so they're asking us to solve this differential equation. So dy dx is 3x squared y. Separate and integrate. 1 over y dy. I'm dividing both sides by y, and I'm multiplying both sides by dx. Now we integrate. Natural log absolute value y is x cubed plus c. Plug, okay, I'm not going to plug in 8 for y, so I'm going to e to both sides. E to both sides. So we get y is equal to c e to the x cubed. Now I'm plugging in my point 0,8. 8 goes in for y, 0 goes in for x, e to the 0 is 1. So my equation will be y is equal to 8 e to the x cubed. 8 e to the x cubed. A. honestly, I haven't done these in so long, so I'm looking at these fresh. At the same time you're looking at them, you guys, I'm looking at these fresh too. Haven't done this in a while. Number 4, consider the differential equation. So they gave us this differential equation, which, by the way, is not separable. So we cannot solve this ourselves, not until you get to differential equations in college. So we can't solve this, but we can see solutions. Even though we can't solve this, we can visualize. I can visualize lots of solutions here. Got these. There's an infinite number of solutions to every differential equation, right? Okay, it says the slope field for the given differential equation is provided. Sketch the solution curve that passes through the point 0, 1. Well, 0, 1 is right here. So remember what we do here. We follow the slope. We follow the slope, right? It looks to me like this is going to be a line, because all these slopes look like they're identical, and they're following that line. So through the point 0, 1, I have this solution right there. I'm going to change colors because they're also asking me to sketch the solution curve that passes through 0, negative 1. Well, here's 0, negative 1. And again, I'm following along the slopes. This is definitely not a line anymore. It's definitely a curve. And this line that we drew in blue, that's going to be like our asymptote for this, apparently. It's going to do that, and then it's going to come down here, something like that. So I'm going to follow along, follow your slopes along. Just like that. You don't have to put arrows, but I do need to see it go all the way through your graph there. Okay? All right, approximate the value of y when x is equal to 1 using Euler's method. 2 equal steps. The initial point 0, 1. The initial point 0, 1. Okay? So we want the y value when x is 1, and we want 2 steps beginning at x is 0. So delta x is going to be a half. Our initial point is 0, 1. And our dy dx is given to us with an equation. So step 1, dy dx at our initial point is going to be 2 times 1 minus 0, so it's going to be 2. Y minus the y value is the slope times delta x. So y will be 1 plus half of 2 is 1. So our first stopping point, f at 0.5 is approximately 2. Now we find our slope at that new point. So 2 goes in for y, and a half goes in for x. So our slope again is 2. Y minus the y value is the slope times our delta x. So y is going to be 2 plus half of 2 is 1, or 3. And so when x is 1, I'm answering it in the form that they asked me. When x is 1, y is approximately 3. Okay? All right. Part C. Find the value of b for which y equals 2x plus b is a solution to the given differential equation. Well, if y equals 2x plus b is a solution to this, then if I take the derivative of this, it has to be that, right? So the derivative of this is 2, and I'm going to set that equal to 2y minus 4x. Okay? I'm going to take this and solve it for y. Why am I solving it for y? Because y is solved for right here. So I'm solving this for y. I'm just going to add 4x to both sides. And now I'm going to take half of both sides and move this around like that. So let's see what we have. We have y is equal to 2x plus b, and we have y is equal to 2x plus 1. So what does b have to be? B has to be 1. Okay? All right, let's see. Part D. Let g be the function that satisfies the given differential equation with initial condition 0, 0. So that would be this curve. I can see the curve. I don't know the equation of the curve, but I can see it. Does g have a local extremum at the point 0, 0? If so, is the point a local max or a local min? Justify your answer. Okay. Well, at the point 0, 0, dy dx is equal to, I'm putting 0 in for x, 0 in for y, 0. So it might be a local extremum. It might be a relative min or a relative max, but it might not be. How can we find out if it is? How could we find out? All we know right now is that g has a critical number of 0, right? Well, I think the way I'm going to do it is I'm going to go ahead and do the second derivative test. So we have our dy dx, and I'm going to come and I'm going to take the derivative of both sides with respect to x. If I do that, I get the second derivative is equal to 2 dy dx minus 4, right? At 0, 0, the second derivative is equal to 2 times, you guys, what was dy dx at 0, 0? Well, we already found that. It was 0. Minus 4, this is negative. Dy dx is 0. The slope is 0, so the slope of g is 0 there, and g is concave down there. Concave down and a slope of 0 means we have a relative max. So therefore, g has a relative max at 0, 0. And again, this is since dy dx is 0, and the second derivative is negative at 0, 0. Okay? Nice little, that's a nice little FRQ. It had a lot in it. We never did solve the differential equation there because we couldn't. Okay? All right, number 5. Let's see, dy dx is y secant squared x. Y is 5 when x is 0, then y equals what? They're asking us to solve this differential equation because we're trying to get y. So separate and integrate. I'm going to divide both sides by y, multiply both sides by dx. We separated, now we integrate. Natural log absolute value y is equal to the antiderivative of secant squared x is tangent x. Okay? E to both sides, and we get y is equal to c e to the tangent x. Now we're going to plug in the point 0, 5 to find c. We get 5 is equal to c e to the tangent of 0. What is tangent of 0? Well, tangent of 0 is 0. So e to the 0 is 1, so we're just getting c there, and we get y is equal to 5e to the tangent x. That's c. All right. Again, we're asked to find y. We're given a differential equation. We're asked to find y. And they give us an initial condition so that we can, this will help us find c when we're, after we integrate. Okay, so I'm dividing both sides by y squared, multiplying both sides by dx. I separated, now I integrate. This is not a natural log, so don't tell me that that's a natural log. The antiderivative of 1 over y squared is negative 1 over y. Okay? If you don't know why that's true, you're changing that to y to the negative 2 and using the power rule. The power rule gets you negative 1 over y is equal to 1/3 x cubed plus c. Okay? And I think I'm going to go ahead and multiply both sides by a negative 1. Negative 1 times c is just another constant. And now I think I'm going to plug in my points. So I'm plugging in 1, 1. So I get 1 is equal to negative 1/3 plus c. I'm adding 1/3 to both sides. So c is 4/3. And now I get this. Okay? Now I get that. Last step is to solve for y. Solve for y. Well, when we solve for y, think of it as I'm multiplying both sides by y, and I'm dividing both sides by this. So y will equal 1 divided by all of this. And that's a safe stop plot. I will tell you guys, I don't know how many times on here I see kids, when they go to solve that, they flip it. They know they're flipping y, so they want to flip each piece. You don't flip each piece here. You have to take 1 over the whole thing, all right? It just doesn't work that way. It doesn't work taking the flip of each piece. Okay? Now, if you wanted to here, we could multiply top and bottom by 3, and that would get us 3 divided by negative x cubed plus 4, or 4 minus x cubed, and that looks a little bit neater, but safe stop on that. Okay? Oh, they did want us to find y when x is 2. We want to find y when x is 2. So when x is 2, I'm going to say y at 2 is 3 divided by 4 minus 8 is a negative 4. So we get negative 3/4. I forgot that this was multiple choice. Okay. This is a multiple choice one. So negative 3/4 is D. Okay. All right. Okay, we got a nice little FRQ here. An increasing function f is increasing, satisfies this differential equation, gave us an initial condition. Use the tangent line to the graph of f at x equals 0 to approximate the value of f at x equals 1/4. Okay? They're asking us to use a tangent line. Did they give us a tangent line? No. That means we're going to have to find the tangent line. They're asking us to write the equation of the tangent line and then use it. All right? Well, writing the equation of any line means we need a point and we need a slope. Right? Well, the point they gave us was when x was 0. The point was when x is 0. What's the y value when x is 0? Well, they gave it to us. It's 1400. So essentially they gave us the point. Did they give us this? oh my gosh. Essentially, they gave us the point. I don't know why I wrote it down there with slope. Okay. The slope, did they give us a slope? Well, almost, because they gave us the equation for slope. So dy dx at our point is going to be, okay, we're putting 1400 in for y. There's no place to put the 0, right? That's okay. But we're putting 1400 in for y. That is 1/25 times 1100. So how many times does 25 go into 1100? I would probably just save stop and leave it there, but let's see. It goes 44 times, okay? Because there are 4 25s in each 100, right? And we have 11 of those. And 11 times 4 is 44. All right, I had to talk myself through that. All right, so the equation of the tangent line equation is y minus the y value is the slope, oops, times x minus the x value. There's the tangent line equation. And now we want to approximate the value of f. So if we solve this for y, we would get the approximate value of f, right? The approximate equation for f when x is 0. When x is a fourth, when x equals a fourth, I need to stop because I keep making mistakes with my writing. When x is a fourth, y minus 1400 will be approximately equal to 44 times a fourth minus 0. Okay, so f will be approximately equal to 1400 plus 11. Okay, so f at a fourth is approximately equal to 1411 if I don't save stop. All right, find the second derivative in terms of y. Well, they gave us the first derivative. To find the second derivative, we take the derivative of each side with respect to x. So I get the second derivative is equal to, okay, I need the derivative of this with respect to x. If you distribute the 1/25 through the parentheses, you're going to get 1/25 times y, 1/25 times y, the derivative of that is 1/25 dy dx. Then we're going to have to be taking the derivative of 1/25 times negative 300. Well, that's just 0. So this is the second derivative, but it's not in terms of y, it's in terms of dy dx. To get it in terms of y, we replace dy dx with 1/25 times y minus 300. Now the second derivative is in terms of y. Okay? Now it says use the second derivative to determine whether your answer to part A is an overestimate or an underestimate of f of 1/4. Okay? All right, let's think about that. Well, at the point, you agree that what I'd like to do is be able to say something about the concavity. I'd like to be able to say something about the concavity. All right? We know when x is 0, f of 0 is 1400, right? We know it's 1400. And we were given that f is increasing. Yeah? So the second derivative the second derivative, if we put something bigger than 1400 in for y, we're going to get a positive. So that means the second derivative is positive for x bigger than 0. It has to be. It has to be. So since our second derivative is positive when x is a fourth, our second derivative is positive, so our curve is concave up. We used a tangent line to approximate a value. We used a tangent line to approximate a value, so our tangent line is going to fall below the actual curve. Okay? So I'm going to say, therefore, the answer using a tangent line the approximation using a tangent line will yield an underestimate. Since we used a tangent line on a concave up curve. Okay? All right, part C, find the particular solution to that differential equation using your initial condition. Big points. So I have dy dx is equal to this. We're solving this differential equation. So I'm going to separate and integrate. Divide both sides by the y minus 300. Multiply both sides by dx, and then integrate both sides. The integral of the left is natural log absolute value y minus 300. I know it's just that because the derivative of this is just 1. Whenever the derivative is just 1, that's your antiderivative. Okay? On the right-hand side, I have 1/25 x plus c. E to both sides, and we get c e to the 1/25 x. Okay? And again, we can lose our absolute values because the c is going to take care of our sign on y. All right. Plug in your point. So f of 0 is 1400. So 1400 goes in for y. 0 goes in for x. E to the 0 is 1. So our equation becomes this. And lastly, solve for y. And that was what we were asked to do. Okay. Use your particular solution in part C to find the actual value of f of 1/4. Okay, well f of 1/4 is going to equal 300 plus 1100 e to the 1/25 times 1/4. So that would be a safe stop spot. Okay, they want us to use our calculator so that we can compare our answer here to our answer in part A. So 300 plus 1100 e to the 1/25 times 1/4. So that comes out to be 1411.055. In our answer to part A, we got 1411 using a tangent line approximation. So that's not too bad of an approximation. Okay. I'm getting a little hoarse here. But I will continue on. Well, how long is it? Okay, about 40 minutes. Alrighty. I'm going to continue on. A cylindrical barrel with diameter of 2 feet. That means the radius is 1 foot. contains collected rainwater as shown in a figure. This was back from 2019. Number 4, no calculator. I think this is the entire problem. I've already given you a piece of the problem in a test. Now we're going to do the whole problem. Okay? The rate of change of the height of water in the barrel with respect to time, t, is modeled by this differential equation, where h is in feet, t is in seconds, and then they give us the formula for the volume of the cylinder. Okay, part A. Find the rate of change of the volume. What is the rate of change of the volume? The rate of change of the volume is dV dt. With respect to time, when the height of the water is 4 feet. So we're looking for dV dt when the height is 4. So here's our equation for volume. And we're looking for dV dt when h is 4. So I'm going to take the derivative of both sides with respect to t, because that's what they asked me to find. So dV dt is equal to, okay, I'm trying to take the derivative here, and I don't want to take the derivative of this. I want to use something that's going to help me. R here is 1. R is 1 all the time. All the time. So I can just replace R with 1 like that, since R equals 1. Okay? Now I'm just taking the derivative of this with respect to t, which is much more friendly. It's just pi dH dt. Right? And now I get to plug in what I know dH dt is. So dV dt is pi times -1/10 square root h. At h equals 4, dV dt is equal to pi times -1/10 times square root of 4. And I'll say stop there, but we have to indicate units of measure. So let's see. Feet and seconds. Feet and seconds. So V is in feet cubed. T is in seconds. V over T. Feet cubed over seconds. All right? Okay, when the height of the water is 3 feet, when the height of the water is 3 feet, is the rate of change of the height with respect to time increasing or decreasing? Well, the rate of change of height is dH dt. That's the rate of change of the height. And we want to know if that is increasing or decreasing. Well, whenever we're wondering if any function is increasing or decreasing, we take the derivative of that function. So we need to take the derivative of this function and plug in 3 for h and ask ourselves, is the derivative of this function positive or negative when h is 3? Okay? So here's my dH dt. We were given that. We need to take the derivative of that to see if this is increasing or decreasing. So the derivative of this with respect to time will be the second derivative. Okay, taking the derivative of this is h to the 1/2. So we're using the power rule for derivatives. So we're going to have -1 over 20, h to the -1/2, dH dt. Why dH dt? Because we're taking this derivative with respect to t, not with respect to h. Okay, it's implicit differentiation. So now we can say, all right, I'm going to go ahead and plug in This is 1 over square root of h. dh dt is negative 1/10 square root of h, right? What happened to our square root of h's? They canceled out. And I have a negative times a negative, which is a positive. They asked me to plug in 3 for h, but there's no place to plug in 3 for h. So the second derivative is always positive. For all h's, it's always positive. So dh dt is always increasing. Okay. Then in part C, at time 0, the height of the water is 5 feet. Use separation of variables to find an expression for h. How nice of them to tell you what to do. Separate and integrate to find h. So we're solving this differential equation. Separate, integrate. Divide by square root of h. Multiply by dt, integrate both sides. I'm thinking of this as h to the negative 1/2. I'm thinking of that as h to the negative 1/2. So it's going to be h to the positive 1/2 because we add 1 to the exponent, divide by 1/2, which is the same as multiplying by 2. The derivative of this side is negative 1/10 t plus c. Okay? Now I'm going to multiply both sides by 1/2 to get rid of this 2. So I'm going to have h to the 1/2, or square root of h, is equal to negative 1/20th t, yes, plus 1/2 times a constant is just another constant. Okay? Time to plug in. At time 0, h is 5. So h at time 0 is 5. That's what I'm plugging in. 5 goes in for h. 0 goes in for time. So c is the square root of 5. So I get the square root of h is negative 1/20th t plus square root 5. The last step is to solve for h. So we're squaring both sides. And that's it. So, how did they score it just 2 years ago? Just 2 years ago. Not very long ago. This is how they scored it. 1 point for your separation of variables. Separating, got them a point. 1 point for the antiderivatives. The 2 antiderivatives. That was 1 point. Okay. 1 point for the constant of integration and using the initial condition. Using the initial condition and having this plus c. That got another point. 1 point for the equation in terms of h and t, and then 1 point for solves for h. This was worth 5 points that year. Solves for h. 1 point for just putting the c value in, and then 1 point for finishing and solving for h. 5 points. Part B was just worth 2 points. 1 point for your answer, and 1 point for the explanation, which would be the whole thing. So that was worth 2 points total. Part A was worth 2 points. 1 point for finding dv dt, and 1 point for the answer with units. Answer with units. Okay, very good. Good stuff. Big points and good stuff. All right.